Hi there. This video is going to walk through some basics of multi-component phase diagrams and the process of distillation. Let's start by considering an ideal solution of two volatile liquids that have unique boiling points. Over here, we can look at a breakdown of what the process we're interested in is going to be. Okay, so here we start off with pure liquid A and B mixture, okay, of some given composition. Okay, so the blue square here indicates, or I should say maybe not pure liquid since we have a mixture, but let's just say that that is all liquid. So everything in our mixture under situation X is going to be all liquid phase. Okay. As we begin to heat up our mixture, okay, so here we're increasing temperature as we go across from X, Y to Z. Okay, as we start heating, we're going to start to vaporize our multi-component mixture. Okay, so then we're going to have some portion of our mixture that is in the vapor phase and another portion that is in the liquid phase. Okay, so the green circle will indicate for us the vapor phase of our mixture of A and B, okay, and the blue circle will indicate the liquid phase of our mixture of A and B. And then as we continue to heat our mixture, okay, at some point everything will vaporize and we will have entirely vapor phase. Okay, so the green square is going to represent all vapor phase. Okay, and just again, remember that the situation that we're talking about here is an ideal solution. Okay, we'll talk about how things change a little bit when we have non-ideal or real solutions. Okay, but right now we're focusing our discussion on ideal solutions. Okay, so the next thing that we need to think about is distinguishing between A and B. So what we want to do is to figure out which one of those has the higher vapor pressure, okay, or the lower boiling point, okay, or vice versa. So we're going to say for our example here, let's say that component B has a higher boiling point than component A. Okay, so in other words, we're saying that A is the more volatile component in our example. Okay, and we're also going to assume that we're working at normal pressure, so we'll say 1 atmosphere or 1 bar of pressure, and that will allow us to basically make this plot a plot as a function of the normal boiling points of the components of our mixture. Okay, so we will assume 1 bar of pressure. Okay, so what is nice is that we can predict the average equilibrium composition of our liquid and vapor phases of the solution as a function of temperature using what we call a temperature composition diagram. Okay, so that's what we're going to set up over here. So we have temperature on our y-axis. Again, we're going to, assuming that we're at 1 bar, this is going to essentially represent our normal boiling points. Okay, and then our x-axis is going to be as a function of our more volatile component, our lower boiling point component. So in our case, we're going to plot this as a function of the mole fraction of A. So as we go across our x-axis, we are getting a higher composition in A. Likewise, if we go in the other direction, we have a higher composition of component B. Okay, so here we have all B, and at this point, we're going to have all A in our ideal solution. Okay, so first thing we want to do is to get a relative sense of the boiling points for the different components in our solution. So we've already said that the boiling point for B is going to be higher. Okay, so we're going to start up here. We'll say that that is our boiling point for B, and we know that A has a lower boiling point. It's our more volatile solution. So that's going to, when we have all A, that boiling point is going to be a bit lower. So we will say boiling point of A down here. Again, this is all approximate. If you have a specific solution, these would just represent your normal boiling points of each component of your mixture. Okay, so you would have some sort of data or information about how your boiling point changes with respect to your solution composition, your mixture composition. You would collect that data, so we'll just put in the basic shapes that you will, shouldn't have that little wonky down there. Okay. So just put in the basic shape of the curve that you would expect, and then we would have that. Okay, so let's just label the different parts of this temperature composition phase diagram so we can be clear about what each region represents. Okay, so the way that we've set this up, we're going to have the liquid phase is going to be in this lower region, and the upper phase will be our vapor. Okay, and this region in between is going to be where we have a mixture of the liquid and vapor. Okay, so kind of comparing to our picture that we discussed over here, this is where we would have our blue squares. Okay, so we can make this the blue square region. So that's all liquid. Okay, and then we have all vapor up here. Okay, that would be our green square region, and then in between we have our circles. Okay, so there's a green circle and then our blue circle. Okay, so just kind of matching up with the pictures that we put together on the left. Okay, and just another quick note about what these lines represent on our plot. So what we have here is this is essentially the boiling point of your mixture as a function of the vapor mole fraction of component A, and then that lower one is going to similarly be the boiling point as a function of the liquid phase mole fraction of component A. Okay, so that's what where those lines come from, the data for those lines. Okay, so now that we've set up our temperature composition diagram for a sample mixture of component A and B, now we can see how we can utilize these types of figures. Okay, so just as an example, let's say that we start with a pure liquid composition that is 0.6 in mole fraction of A. So let's say we start there. Okay, so what will happen is as we increase the temperature of our mixture of components A and B, starting with a composition that is 0.6 mole fraction in A, as we heat up, we're just going to move up this line. Okay, so in this region here, we still have all liquid. Okay, so we're still in our square region where we have all liquid A and B. Okay, so everything's still a liquid as we increase the temperature at this constant composition of 0.6 in A, okay, 0.6 mole fraction in A, and we're going to keep going up until we hit this line. Okay, so we'll increase our temperature, and then once we hit this temperature, that matches up with that point on our liquid vapor line, the lower liquid vapor line, we are going to get our first vapor. Okay, so at this point, go up here, this is where our first vapor appears. Okay, so now we're at the point, we're entering into the point where we have a mixture of vapor phase A and B and a liquid phase A and B. Okay, so we can continue to heat beyond this point. Okay, so again, we're staying at constant composition here for a mixture. We're just heating that. As we continue to heat past that point, so now we're in the liquid vapor equilibrium region. Okay, so let's say we heat to this point right here. So what's happening when we heat up to this temperature? Okay, well, the real utility of these types of diagrams is that they allow us to predict the compositions of the liquid and vapor phases for our mixture at a given temperature. Okay, so what we're going to do is, so we've gone up in temperature to this point, what we're going to do is make what we call a tie line. So I'm just going to kind of go over here and then over to the right. Okay, and those new dots will tell us the overall new composition of the liquid and vapor phases at that new temperature. Okay, so as we go over to the left, as we follow that tie line over to the left, okay, so we'll just go this way. Okay, where we intersect that lower curve, liquid vapor curve, okay, is going to correspond to the composition of the liquid at that, I'll just say that's at T prime. Okay, so this is the composition of the liquid phase at our new T prime. Okay, and likewise, if we go to the right, if we connect that tie line to the right, okay, and then where we intersect with that upper liquid vapor line, that's going to correspond with the composition of the vapor phase. At that T prime. Okay? So again, this temperature composition diagram is just a nice way to help us predict what the relative compositions of the vapor phase and liquid phases are going to be as we heat up our solution. Okay, so again, just following up as we go up in our constant composition. Remember, we started at 0.6 mole fraction in A. As we heat up, okay, here we've reached the point where we start to form our first vapor. Okay, and as we continue to heat up our solution, okay, we can predict the relative composition of the liquid and the relative composition of the vapor by just kind of drawing that horizontal tie line, okay, and that will correspond then to the relative compositions of your vapor and liquid. Okay, so again, this part right here, this is what we call the tie line. All right, now let's keep going. As we increase our temperature further, okay, again, we'll start to, you can predict your compositions as you go up, right? Just draw your tie line in there, okay? And then at a certain point, we'll hit a temperature where we will essentially evaporate our last liquid. Okay, so once we get up here, this is where our last liquid disappears. Okay, and then as we continue heating, we're just going to have basically heating our liquid. Okay. Sorry, heating our vapor. So our last liquid disappears, so now we've got all vapor, and we will continue just heating up that vapor. All right, so as we heat the solution, okay, we can see that we get a vapor as we start heating up here past this lower liquid vapor line. We get a vapor that is enriched, relatively enriched in A, okay, and a liquid that is more enriched in B, okay. And then as we keep heating, right, it actually gets a little bit less enriched. That vapor will get a little less enriched in A and even more enriched in component B. Okay, so I hope that was helpful in kind of how you want to interpret these temperature composition diagrams and how they can be helpful. Again, their utility lies in being able to predict the relative compositions of your vapor phase and liquid phase as you heat up or cool down your multi-component mixture. And in case you haven't had enough fun with this, you could also plot what we call a pressure composition diagram. Okay, so you get the same kind of information, except instead of plotting as a function of temperature, maybe you're interested in seeing how things change with your multi-component mixture as you change the pressure. Okay, so here we were assuming a constant pressure of 1 bar. Okay, so we can change the pressure instead. So we would have pressure on our y-axis instead of temperature. Okay, but just remember that your vapor and liquid regions would be inverted from what we see here. So you would have vapor on the bottom and liquid on the top, since a lower boiling point is going to essentially correspond to a higher vapor pressure. Okay, so things are going to be swapped around if you want to make a similar plot for changes in pressure.